Hi everyone, today we'll be talking about multi-version concurrency control. This is the agenda for today. First we will talk about what is MVCC, then how is concurrency achieved in DBMS, the need for MVCC, demo, limitations, and finally conclusion. So what is MVCC? It is known as multi-version concurrency control, and in short, MCC or MVCC. It is basically using the concurrency control method, and this approach is commonly used by database management system. MVCC provides concurrent access to the database as well as in programming languages to implement transactional memory. So here are some of the database that uses MVCC. MySQL, which is a very commonly used database, SAP HANA, Microsoft SQL Server, and lastly PostgreSQL. This will be used in our demo later on. Now we'll be moving on to how concurrency control is achieved in database.
MVCC is designed to ensure that users do not block writers from writing to a database, and writers that read it on the same record does not cause a conflict. This is achieved by using data versioning and snapshot isolation for concurrent users. Now let's assume if person A is reading from the database at the same time as person B, who is writing to it. It is possible that the reader, which is person A, will see a half-written or inconsistent piece of data. The simplest way to prevent this is to implement locking, where it blocks readers from reading until the writer is done editing. However, this can be inefficient and prevents concurrency. So, MVCC takes a different approach whereby each user connected to a database see a consistent version of the data at a particular instant of time. This method is called snapshot isolation. Any changes made by a writer will not be seen by any other users of the database until the changes have been made. This allows readers to continue reading while not preventing writers from writing. Also, changes that is made on the same record will be stored as a new version, and the previous version of the record will not be overwritten. This allows users to be able to revert back to a previous version, keep track of changes that has been made, or identify who made the change.
Without MVCC or any form of concurrency control, collisions happen. Collisions happen when two activities attempt to change entities within a system of record. A dirty read happens when user A reads an entity from the system of record and then updates the system of record but does not commit the change. User B reads the entity, unknowingly making a copy of the uncommitted version. When user A rolls back to the original state, user B now has a version of an entity that was never committed and is therefore not considered to have actually existed. A non-repeatable read happens when user A reads an entity from the system of record, making a copy of it, and then user B deletes the entity from the system of record. User A now has a copy of an entity that does not officially exist. Lastly, a phantom read happens when users get different sets of results on separate occasions because new entities are added to the system by different users. Therefore, it's important to have MVCC because MVCC complies to the ACID properties. The ACID properties are deemed as properties of reliable database transactions. Atomicity can be achieved because most databases implementing the MVCC feature would store a version of the system of record. Consistency can be achieved since each transaction would be done on an isolated snapshot version of the database. Therefore, there will be no corruption of data or replicates having same data. Isolation is achieved since every user gets a copy of the consistent version of the snapshot. All major databases today would write to disk so as to achieve durability. Moreover, MVCC provides more concurrency since every user or thread is working on a separate snapshot of the database. Therefore, there is no need for read and write logs required, thus making MVCC non-blocking.
As my team members have covered what is MVCC and how it works, I will be conducting a live demonstration of the MVCC features using PostgreSQL. Since PostgreSQL uses the technique of MVCC, in PostgreSQL, the database creates new copy of modified rows Other users do not have access to modified roles until they are committed. And once committed, the original roles are marked as obsolete. So the first top left SQL shell that I've opened up, it shows the sequence, the tables, and I have inserted some sample data inside here. As you can see, Pamela, Jinhui, and Gary. Okay, so for now I'm going to close this shell. So this shell over here is client 1, this shell over here is client 2, and this shell over here is client 3. So I have opened up 3 PSQL shells at once, representing 3 different clients to demonstrate in this live demo. So right now, in client 1, I'm going to start by inputting the SQL statement. So client 1 starts reading school data from the database by begin. So we're going to set transaction isolation. Okay, and I'm going to select star from the school table, order by school ID. So you can see over here the school ID 1 and 2 represents SMU SIS and SMU School of Business. So now let's head over to client 2. So for client 2, the client 2 wants to update student data in the database. So same thing here, begin. So I'm going to select star from student, order by student ID. So over here you can see the student ID 1, 2, 3 representing Pamela, Jinhui, and Gary, followed by their school ID. So I'm going to update the student, and I'm going to set the student name to Xuening, where student ID equals to 1. So I have already updated the student ID 1 to Xuening. So in client 3, the client 3 will not be able to see the changes made by client 2 over here because client 2 has not complete the commit function. So I'm going to demonstrate to you. Select star from student order by student underscore ID. So you can see for client 3, you can see that the names is still Pamela, same as for client 2. So now at client 2, I will commit, and it states that it's commit. So now when I go back to client 3, I select star from student table and sort it by order by student ID. You can see that now after committing, after client 2 has committed its change to the student data, client 3 can now see the changes because they have been committed. As you can see over here, compared to here. Okay. And do note that if I go back to client 1 and I select star from student table order by student ID, it will still show Pamela instead of Xuening because Postgres is presenting it with the database state as it was when it started the transaction, or in precise term, as it was when we first did the first select. Note that this is the first time this client has read the student table, And now I have end my demonstration.
So let me talk more about the limitations of MVCC. So MVCC require more space to store different versions of the data. This happens because different transactions will have visibility to a different set, item, and versions. So all versions are stored in the same key value space, and there is no fixed limit on how many versions may be maintained. So the old versions are collected by a background process that is executed continuously by schedule or by trigger, by read or write. So the next thing is actually some data cause an update conflict, updated by two different transactions at the same time. So the primary key values space stores only the latest version. So the previous versions are stored in another fixed size storage. The last version have reference to the previous versions, and particular versions can be tracked back by transactions that require them. So because size of the storage is limited, the oldest version may be eliminated to free for the newer free space for the newer item. So if some transaction is not able to find a required version, it fails.